Hello everyone, welcome back. Today we have G4 of ELMOSL Shortlist 2019, and essentially what I'm doing today is I'm putting my legacy on the line. What I mean by that is I don't know the solution to this problem yet, and I'll be trying to live solve it again. Why do I do this? Because I'm just searching for trouble, I guess, and just waiting for the moment that I will manage to solve a question while trying to do it live. I just did the sketch, and well, I'll try to solve this, and either I'll solve this and my channel will be um, growing, you will put likes and say that I'm cool in the comments, or I'll absolutely embarrass myself and not going to solve this question, and you're gonna put dislikes and hate on me in the comments, which will be absolutely fair, and I'll probably delete my channel. So let's just hope that I will be able to solve this question and solve this question not in a very long time because it's kind of late and I low-key want to go to bed. But yeah, sorry that there was a bit of delay in the videos. I know I promised to drop a video last week, but I got like sick and yeah. So here's the problem. We have a triangle ABC with attitudes BE and CF, which meet at H, and the reflection of A over BC is point A prime. The circumcircles of AA prime E and AA prime F intersect the circumcircle at P and Q, and BC and PQ meet at point R. We need to show that HR is parallel to EF. Okay, I can delete this problem. Thank you to Daniel Hugh for deleting this problem. So, we have quite a bit of two things that we can talk about, especially this problem. So the first drops in my mind is obviously like these circles AA prime F and AA prime E. If you watched my videos on the good point, bad point method, then we know that like A prime E and F are all pretty well defined, and it's like the problem is getting to points P and Q, getting to know them better, and so on. So that'll be like the main problem, I guess, when trying to solve this. Um, but yeah, I mean, let's have a think. We need to show that FE is parallel to HR, which is like the same as maybe showing AO is perpendicular to HR. So if I take a point here, mark it as mark it as O, and then essentially I know that by taking the antipode, let's call it A0, this, and I call this antipode A0, and then I intersect right here, and I intersect segments AO and BC at point, let's call it D. For the point D, I know that for triangle ADR, H is the orthocenter. This is like a very popular trick that's used sometimes in these kind of configs. Maybe it's not useful, maybe it is, but um, I'll just drop it in for the sake of dropping it in. Maybe it will help, maybe it won't. Um, but yeah, we need to start like developing our understanding of what's actually going on because so far it's kind of these points P and Q are like hanging in the air. So we probably want to sort that out first. Um, and the way I think we can sort it out is maybe by simple angle chase as well, because we know that these land on line, for example. So maybe if I draw a prime P, it'll pass through something nice. Or it won't. Yeah, I don't think it passed through anything nice, chat. Don't think and go through anything next. Well, the other thing is that if we intersect AR with the circle at a certain point, let's call this point S. What it not? We just like we know that DH should be perpendicular to AR. DH and AR. Okay. Um. I mean, we kind of do have to get to know points P and Q sooner or later. So, and there's kind of these rad axis stuff going on. So maybe we should find a circle that passes through PQ, through H. I don't think there's anything that passes through H. Maybe the Humpty point though, but okay, so okay, let's think critically. If we have circle BHC over here, right? Then we do know that this line here is a tangent, because FE is anti-parallel to BC. So essentially, we just want to show that the tangent here and PQ intersect on BC. That's really slightly better because I think, well, I know that's just equivalent of showing that HPQ is tangent to the same thing. That's just using logic. Maybe we don't need these at all, so I'll delete them for now. So, as we see, we just need to show this thing over here. Yeah. The other thing is that mm, we'll probably redefine our stuff. So if I go like, ooh, doesn't like this. Yeah, it doesn't. Well, if I try to redefine the problem statement for triangle A prime AC, um, maybe it will turn out nicer because I'll have this tangent to H and reflection, two circles, which is like semi-nice, I guess. It's not like amazing. Um, we do know that R this thing. So if I take point N, intersection of AH and the circle of triangle ABC, this, oops. If I take this point here, then this will be also tangent, just by power of point. So, and we need to like kind of, we can kind of, I guess, forget about the circle and just focus on HPQ. So, yeah, I mean, we kind of want to show that these lines are one line or that HPQ is tangent to BHC, which looks kind of, yes, too much for now. The only maybe like logical extension would be intersecting here and hoping that this point is kind of nice. Um, but if it's not the Humpty point, then yeah, there's no hope. But I think it is the Humpty point, so I think it's safe. Oh no, it's not the Humpty point. Never mind. Yeah, I mean, not the Humpty point, so kinda unlucky. Sure. I mean, we do want to get close to P and Q in some way, which is annoying, which is annoying. We need to figure something out. So, I mean, okay, let's start with something like, okay, we know that Rn should be a tangent, so I think we can just forget about H, forget about these two heights, take that these F and E are foots of heights, take these two circles, and show that PQ and tangent at N intersect on BC. That will be absolutely enough. So we're trying to kind of like work our way through simplifying the question a bit and breaking down like getting rid of essentially useless points. So this is our new problem statement with Rn being tangent, BQ, and BC being concurrent. Okay. Maybe some Pascal, but that looks kind of weird. Um, yeah, that low key looks weird. Um, hmm. I mean, I kind of do want to get rid of point A. I really do, because these circles are getting like these circles, like the big ones. These are the annoying parts in our problem, and we kind of want to understand what P and Q are really about. And there's too much symmetry, essentially, like too much symmetry with like orthocenter and the opposite point. I would probably want to get rid of A prime though. I would prefer getting rid of A prime. So I need to redefine point P without A prime. That's probably one of because that will help us to get rid of this goofy point and just continue with solving the question. I mean, we also need to do it in a sensible way. So we don't want to do it absolutely terribly, such that like there's a bunch of new points that are even worse. Like, why did we even do this in the first place? Okay, maybe some angle chase. I don't think so. Or maybe. Okay, we still didn't use that these are heights. The ENCF. And since we will probably have to use this at some point, I'll probably just return them back like this. Um, Maybe inverting at H is a good idea. Let's just think about it for a second. In center, ABC, these points will go into IA and IB. We have essentially like this point, this goes to the foot of bisector, I guess. Okay, this is still pretty weird, even for in center, I think. So I won't do that. I mean, okay. Hmm. Let's just try to make some stuff where just draw some lines, build some theories. Okay. Boom. Okay. I mean, triangle ABC, we do have that. Okay, we still didn't use that these are heights, neither did we use the A's, the reflection yet. So we probably want to do something with that. The other thing is that we kind of want to do it carefully as well, um, which is a problem in this case. There's not much of stuff you actually can do. I mean, yeah, there's just not that much information you can start from. I mean, we can start by looking at this angle here. If maybe like some smaller angle chase will give us something, but like this angle here, right, is the same as this angle here, which is the same as this angle here. And I don't think that that's good. Yeah, I mean, doesn't give us much, does it? Just gives us the this segment over here is the same as like this segment here, which still doesn't give us much. So yeah, not a very clear sign of how to deal with the points P to Q so far. But we're gonna continue thinking about it. I mean, it looks pretty interesting. It looks pretty interesting. Like, you maybe want to do inversion at A, just invert it. But to be honest, I'm a much bigger fan of like thinking how to work through such constructions, because it's usually more helpful when you solve other questions. I mean, inversion at A probably should work. Okay, look, should work. Let's just do inversion at A. I can't be asked to think of something else. Okay, so let's do inversion at A. That will swap B and F, C and E, right? So if we have point N, that's circle BAC, will go to circle A to line FE and on AN. So essentially, if we draw this line here, this is our N prime. Okay, tried something smart. Now let's just go to use the dark side. Just try to finish this up quickly because I really can't be asked to think of something smart. Um, yeah, and then A prime. Um, where does that go? Well, H goes into here, so it'll be the midpoint of AH, where H is the orthocenter. So if this is the orthocenter H, why is it not in capital letter? Um, so if this is the orthocenter H, A prime would go into midpoint of AH. Let's call that F. All right, we did have F already, so let's call that K. We don't have K. Okay, and that should be true. A prime B. Okay, yeah, everything is. So, and then we have circle. ABC will go just to line FE, obviously, and then if we take a look at AFP A prime, then it'll be a line through image of F and image of A prime, which is PK. This line here, and CK, and it will intersect at points that are images of P and Q. So, yeah, yeah, but I'll just bash through version. Like, I usually think that's shameful. In this case, sorry guys, I'm already tired. I would like, I'd rather, I would rather sit on this construction and think how to do it without inversion than doing with inversion. But here we are. I have school tomorrow, so no, we'll just do it this way. Okay. And then we have just tangent here and M, PQ, and BC. So what does it want us to show? Well, we essentially wanted to show that NPQ and BHT were tangent, which is equivalent to, we wanted NPQ, which is essentially FE, and circle PHQ. So PHQ goes into here. So if we have this, this, that's our image of, we wanted HBC tangent to HPQ. Oh yeah, and HBC goes to this thing. So we want these two circles to tangent. They are tangent. Toot, toot. Yeah, they are tangent. Alright, this seems much better than we had because this circle is actually the Euler circle. So this is how like we got rid of these two circles. The reason why I thought inversion at A, I actually thought about from the beginning. I just am not a big fan of inversionists, if I'm honest. I just prefer not to do it. But yeah, it does work in this case because these circles are pretty random. And if you take inversion at A, P and Q will be mapped to better points. So now we're left with a better problem. Let's just quickly rip it, rip through it, and just obliterate it as fast as we can. So we have these two circles, this height here, just, and I'll just repeat everything we discovered so far. So we have triangle ABC, three heights DEF. K is the midpoint of AH, and then obviously DEFK is the Euler circle, so they lie on one line. And we have N prime intersection of FE and AD, and then we don't even need it anymore. And then we have P prime and Q prime be the intersections of BK and CK with a line FE. Yeah, and then we want to show that circle through D, P prime, and Q prime is tangent to the circumcircle of DFE. Okay, let's not rush now. Oh, my voice is getting so much worse. My voice, but we want to show that these two circles are tangent. Oh, oh my goodness. Okay, uh, let's have a little think how we want to show that. Okay, so I think I have a slight idea. And the idea is that essentially we want to show that d for this angle p prime dq prime, dh is the angle bisector. If we show that, then we're done. Because there's the famous lemma that if you draw these two things and these two are equal, then this is tangent. And since dh is the bisector of angle FDE, then it should be the bisector of P prime D Q prime, and we will be done. So you just want to show this. And there's another famous lemma, and the lemma states the following. Let me just, I'll actually, one second. So just added another setup for my pen. And essentially, there's this famous setup where you have a triangle ABC and a random point on the height, and then you draw two lines like this, not necessarily the other two heights, and there's a claim that these two angles are equal. And the way this lemma is being proved is following. Let's take two points here such that these two are equal, and these two are equal as well. And if I look at this angle here, this angle here, by the second isogonal lemma, I know the intersection of this and this, and of this and this, are isogonals of that angle, so they lie on the bisector of this. And so we're done. And this is a very useful lemma over here. And if we look at triangle KBC, we can see that these two angles should be equal and lie on the height here. So essentially what we just want to show is that BQ prime and CP prime intersect on the height. And that's essentially all we need. So now we got rid of all of this thing. Wait, I get rid of this. But okay. I think that's fine. The other thing is that I do believe this claim should work for any like this point in the height. So if I take this in here and this in here, oh my goodness, this point here, oh, this is annoying. They should intersect in the height, yeah. So we don't really need that this point K was something. It's just always true. Um, so we just want to verify that if I have like this thing here, it's just any random point K and two lines like this, then these two lines intersect on this line over here. And yeah, that seems like pretty simple to do. I don't think that will be too challenging. But I think the quickest way might be with like projections and stuff. So there might be some like moving of points method, but I think that if I take just a point H here, let's call it, I don't know, T. If I take point T here, then essentially, yeah, yeah. This is game over for this question. I mean, we're too good. Okay, so if I take another point and call this U, then essentially we knew that since FHC and BHE like intersect here on H, we knew that TBDC is a harmonic quadruple. And then, so if I take this harmonic quadruple and project it through point K onto line FE, I will get points T, I will get points P prime, U, and Q prime. So they should be a harmonic quadruple. And now I project from K this onto BC, the same harmonic quadruple. Oh wait, should I even? Yeah, I don't. That's the same. So we take this already, the new one over here. We know that since this is a harmonic quadruple, then these three should intersect in one point. So we are done. And then by the isogonal lemma, those two angles are equal, and so on, so on, so on. Yeah, I mean, that was pretty close to embarrassment. I don't know. I fumbled around for maybe like 20 minutes doing nothing. But yeah, I hope that was useful for you guys to see how I approached this problem and how I thought about it. Um, if you have any like video suggestions, drop them in the comments. And yeah, thank you everyone for joining in. And have a blessed day.